Well, I'm glad you guys like it. Or at least Allie does. Morning, Eric. Morning, Kimmeline. Morning, Kim. Morning, Charlie. Charlie, don't pull on Eric. Go fill out your attendance form. We know you're all here. So we didn't mark you absent, Eric. But Charlie, still do the same thing. Fill out the form. Really quiet? Shouldn't be. Want me to yell at you? Is that better? Looks like the volume is pinning. Maybe your own volume's... No, that's too loud. I can't hear myself, but I can see the volume meter. Turn your volume up. Morning, Ava. I don't know if I missed you. Alright. So our agenda today is taking DNAQ 25 and then doing the first half of phase 3. Alright. You do not need to finish phase 3 today. You don't need to finish it over the weekend. Just have part of it, half of it at most, done. We'll finish it on Monday. Tuesday, we'll work on phase 4. Wednesday, we'll finish phase 4. The document will be done. You turn it in before midnight. I grade it according to our new 24-point rubric, which has 4 strands about making a claim, a direction for the application, gathering information, assessing information, and then being able to come up with a final defense, so your final summary. And then I'll be grading your vocab and your convention. Can you hurry up? Ms. Kilduff says we want to be done soon. Psh. Yeah. Ms. Kilduff. Acting like a kid wanting to get out of class. Hi, Ryan. So, before I get into reviewing the DNA, there's a lot of people who, a significant portion, for some reason, think it's easier and they're going to do better by just Googling the question and getting the first thing that comes up. So I know I'm kind of talking to people who don't do that, because a lot of you in the chat or ask me questions actually go back and look at, the notes that we come up with every single day, and I post on Thursdays, or now Wednesdays. But I had a lot of people this week just decide, hey, I'm going to go back to Monday, and I'm going to look up what is the relationship between a planet's mass and its surface gravity. And they literally just paste it into Google, and they take this blurb right here. The surface gravity of a planet or star with a given mass will be approximately inverse proportional to the square of its radius, and the surface gravity of a planet or star with a given average density will be approximately proportional to its radius. You guys know what that even says? Do you know what an inverse square law is? Do you know how density and radius is impacted on a planet? I mean, this is why Uranus and Saturn don't follow the relationship that we developed on our own. So I have people pasting that in or typing it in. First thing that comes up from Wikipedia, first of all, as their answer. You're not going to have any idea what the answer is. You're going to not have any kind of preparation for the quiz. So those of you who show up to the stream, good on you, because you know that what we're looking for is, for the most part, there is a positive relationship, because as the planet gets higher in mass, its surface gravity also seems to go higher. There's just 2 outliers. An outlier is an exception, that being Uranus and Saturn, but that's because of their density. But hey, if you guys know what inverse square law is and you understand the ratio between radius and density and surface gravity, I might also just skip to that and go to some kind of like high school or lower college level information because I'm wasting my time because you already know all this really well, right? Those of you that just like to Google and give me that answer right there. So use what I provide to you. We do it for a reason. This is much an exercise in learning how to study and being effective in studying than it is knowing the information. I value the skill highly. Second question. What is the relationship between a plant's mass and its rotational period? Well, for those people who actually, want to use the easy way, and that's working with us and looking at the notes, we see that as mass goes higher, that rotation takes a shorter period of time. All right? Or, the shorter your rotation, the lower in mass you are. They're opposite. So if they're opposite, it's a negative relationship. I did have a couple people make small mistakes in saying that it's a positive relationship because as mass gets higher, rotation gets higher. You got to be careful in your wording. If mass is higher, rotation speed is faster. So if I say rotation speed is faster, then yeah, that would be a positive relationship. But what I gave you in the data table was rotational period, which means how long it takes for this object to spin once on its axis. So the spinning, the duration, the time period is shorter. And that makes it negative. Okay? So mass to the rotation period, the day, is shorter. So it's negative. Okay? Don't just assume I'm asking for, is it a faster rotation? All right? This is a negative relationship because I'm asking for, actually pull up the table. I'm asking for the period. I'm not asking for the speed. Okay? That would be in thousands of miles per hour. There is no miles per hour here. It's in days. So this is a shorter period with higher mass. All right? So short, high, opposite. It's a negative relationship. Outlier there is obviously going to be Venus at 117 days, way higher than any of the other planets. Notice that? 117 Earth days. Venus is an outlier because of that very thick atmosphere acting as like a parachute. It slows it down. It slows the planet moving opposite the atmosphere. It's drag. Okay? And I think that's what we put in our notes. Outlier exception is Venus, the only planet that rotates clockwise due to drag of its incredibly thick atmosphere. And that incredibly thick atmosphere is going to play a role in the third question. All right? What did people put who just decided to Google it because they thought it was easier and they get a better answer? The acceleration of a planet in its orbit around the Sun depends upon the mass of the Sun and inverse square of the planet's distance from the Sun. As the planet moves further away in its orbit around the Sun, the gravitational force exerted by the Sun on the planet decreases. At what point does this talk about rotation? This is talking about revolution, and I had people put revolution in their answer. Not even reading what they were just going to copy and paste. So, for a lot of those people, I put in a comment saying, we make notes in simple terms for you to help you study every day, and that you should go back and look at the notes before the quiz tomorrow. That was last night. This is not going to help you for the quiz later. This is not preparation. This is lazy, and it's not going to help you become a better student at all. Next question. Number 3. What is the relationship between a planet's distance from the Sun and its average day temperature? So now distance and Sun, distance and temperature. The notes we put, well, let's look at the table first. Distance in AU, astronomical unit, the distance from the Earth to the Sun. So Earth is 1 AU. Mars is 1.5 times that. Saturn is almost 10 times the distance from the Sun to the Earth. All right. So this is all in order already. None of these other columns are in order except for this one because it matches the order that we put the table in. All right. So average temperature and sunlight side is not in order. So again, finding the relationship that's going on here, put them in order and determine if it's opposite, the same order, or if it's all mixed up. So when we look at distance versus temperature, from close to far, low to high, and even someone like Jake Rainey yesterday who decided to do high to low, he found out it didn't matter because it's a negative relationship. They'll always work opposite each other. All right. You don't have to give a little frown. You just show that it's just a negative relationship. All right. Hypothesis. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune in order. Find out that the order is basically flipped, except for one planet, that being Venus. Okay? So this is a negative relationship. As distance is increasing, temperature decreases. As distance decreases, then temperature increases. Okay? Just like the other question where if mass increases, rotational period decreases, the time it takes gets smaller, or as mass decreases, then the rotational period gets longer. So smaller planets rotate slow, big planets rotate fast. Why? Because big planets have what we call angular momentum. There's more matter. That more matter is carrying momentum, like a Newton cradle, is able to maintain energy and start moving faster and faster. Okay? Venus is the only exception because its thick atmosphere acts as a greenhouse and retains the heat, making it the hottest planet's surface temperature in the solar system. Okay? Temperature is much hotter in the core of the gas giants, but we're not talking about that. We're just talking surface. Venus has the hottest temperature. Like some of you did Venus, hot enough to melt many heavy metals, like lead. All right. So we had positive, negative, negative. We talked about mass and gravity, mass and rotation period, and then distance and temperature. The outliers, again, know the outliers. Low density planets like Saturn and Uranus. Then you had Venus and the other two. Venus's atmosphere causing an issue, rotation period, and retaining heat. Okay? But those people that decided to just copy and paste question number 3, what did they come up with? In general, the surface temperatures decrease with increasing distance from the Sun. Venus is an exception because its dense atmosphere acts as a greenhouse and heats the surface to above the melting point of lead, about 880 degrees Fahrenheit. This one ain't bad. Now, you can probably understand this one because it's basically what we say, right? And so I had people then tell me that the insulation of the planet is going to increase 16 times. 4 times it's closer back to the Sun. So I don't know where you found that one. I couldn't find that one on Google, but kudos to you for trying to find something that we talked about. What is an inverse law for those of you that decided to Google it, and those of you who are in chat wondering what they were even attempting to do? An inverse square law is a rule of thumb where it is almost a reverse exponential function. Let me see if I can pop this graph up. So those of you in algebra, and I think math, you're starting to get towards this. Exponential functions start off slow and then they go up really fast, right? If you've been keeping track of the news, COVID-19 was going to be an exponential function, exponential growth. One person infects 4 people and it keeps increasing for every that person infecting 4 more people. Okay? Exponential meaning exponent, right? To the there you go, to the power of 2, right? This is an inverse square law. Inverse meaning opposite. So it's a reverse exponential function. So the decrease or the increase in the distance from the sun, the decrease in temperature, is a negative exponential function. It's going to drop off dramatically and then even out. So, I mean, you can't get much colder than cold, is what the main takeaway there is. You can't get much colder than cold. Once you start losing the heat of the inner solar system, there's not much more heat to lose. There's more heat to lose in Mercury and Venus's orbits than there is in the outer solar system. And that kind of goes back to talking about the Google data center, in that you had an inverse function. There is no such thing as cold, that's right. So there's not much more heat to give off in the outer solar system. There's no more heat to receive. All right? And so your Google data center, you lost heat inversely, exponentially. You lost it reversed as an exponential function. All right? But, I mean, if you guys know that, then, I mean, we should just go on to some more complex stuff. Right? Goodbye. Any last questions before I post it? Hi, Hike. I think I missed you, Kim. Good morning, Kim. Good morning, Nikolai. No? Those of you that, prepped, I think will be fine. Prepped in the right way. I'm posting from period C, but it should be for all of you. Go right ahead, refresh if you don't see it. Take it, and when you're done, open up the GSA, because I'm going to talk a little bit about phase 3, and then you'll have time to work on phase 3. Where is... There it is. I'm getting it. Wait, what was your background? A little epic jazz. My background's in memoriam from a year ago. I guess I gotta answer my weekly email from Cody asking what time the quiz is gonna be posted at. The kids like the outro. Well, I'll play it when we're done. Gildoff, give me a second. I'll send you a link. This is the numbers and stuff. Oh, okay. There you go. A little too zoomed in. Nikolai, check your email in a few minutes. Fad, how many people take it? 5 people submit? 5 fives out of 5 people? Uh-oh. That usually signals to Mr. G that he put a wrong answer inside the form. So let me just double check before I send this form out to Miss Kildoff. Aha. Yeah, I found the mistake. I bet a bunch of those are going to be 6s. Give it a second. Confirm for me, Nikolai, that you got the email when you got it. Next. Let's fix. This. Got the email? Good. Thank you. And all those 5 jump to 6s. Nice. Got a question through email. Check that. Give you guys a little more time. Johnny assumes he has a 6. Well, remember, there's always a lag on the stream. It's like, I don't know, 3-5 seconds. Revisions require an email from you, so then I can tell you on what to take a look at again. And then you answer back to me in the email, and then you can take the form. 14 people. I do want to start talking about phase 3. Give it a few more minutes. If most of you who are watching right now are good, I'll move on. Because people who aren't watching are going to be checking in later. While we are waiting, guys, if this is going to become an issue, we don't have to look and see what other people got. You guys don't talk about it in class. I don't expect you to talk about it now. Alright, so the mighty meetup. Remember, that is tomorrow while you guys are finishing up the quiz. Tomorrow I'll post in the morning a link in the Mighty Ducks Google Classroom. That link will be for a Zoom meeting. Zoom is very similar to Google Meet, except a little more features, like breakout rooms. Breakout rooms are little rooms that you guys can all go into, but it's all in the same main video conference. Alright? A teacher will probably be presenting something on their screen, so you may sometimes see each other, sometimes not, and that's the goal, of seeing each other, but also interacting with each other. Alright, so in the morning, there'll be a link for the meetup with a password. Alright, so a link and a password. You sign in with your Coventry Google account, and then you use the password that's posted to join. Alright, why is it so locked down for a link and a password? Because in the news, Zoom has gotten some bad publicity for not having the best security. So with a password, no one can really kind of guess the URL for our meeting. You have to know the password in order to get in, and it just prevents people from possibly in the low chance of being abusive towards our meeting. Alright, so when you join around noon, wear a hat, make it part of like a, not spirit week, but a spirit day, spirit theme. Okay, in the studio, if you want to join the studio, I'll assign you there. If you can't join it, to Miss Grant's area, learn how to draw the cast of SpongeBob. You want to watch a movie, Onward, with Miss Kildoff, she'll present that on her screen. In the theater, I'll put you in the theater. You want to play against me in categories, ask my wife. I'm not very good. For some reason, I just like playing it. Go in the arena. Okay? And then Mr. Howman will carry on his tradition of the Fun Friday puzzles in the classroom. Okay? Last around 1:30. And we'll hopefully get to do it again. Alright? On the Fridays where we are not doing something new, as long as you're good with your work, you have nothing to really work on, come join in. You guys don't even know what the game is. You guys were talking yesterday. You don't even, you see, what is it? What is it? It's a category word game with a time limit. I don't know where for hats categories. You don't even know what it is. I believe Hayden would know it. You get one letter. I think I've played before. There's a bunch of categories like a sports team, an animal, whatever, right? And we get a word in the beginning, like the letter B, and then you get like a minute to 2 minutes to think of words that begin with B that fit the category. There you go, that fit the category. Yes, yes. All right. So you guys have some idea. It's not a difficult to understand game. I did find a web version of Monopoly, but then only 4 people could play. If you guys got ideas for other things, send them my way so I can check it out. I was looking at more complex games, but they'd probably be blocked. I don't know. Alright, phase 3 time. That's a weird looking guy. GSA number 1, you guys have done phase 1 and phase 2. Okay? Phase 2 for application B is probably the longest part that you're going to be doing if you're doing application B. Application A and C, your biggest phase is going to be this one, phase 3. Okay? So each application takes about the same amount of time and the same amount of effort and the same amount of work, but they have different phases that are more intense than others. Alright, so for A and C, you guys were just doing some research, gathering information, which, is not easy, but it's pretty straightforward. Application B, they had to make their spectrometer, they had to then test it out, then they had to then record and draw and write in the colors with their absorption and then the images, what they looked like. So they were taking pictures or drawings of rainbows across the CD. Alright, and they're going to analyze the rainbows now in phase 3, but they set up the rainbows in phase 2. Alright, so application A, you guys are doing an ACEs outline. Remember, ACEs, the acronym I use to help you remember what goes into a good CER, but then it also, the A, the C, the E, and the S, they all correspond to basically each of these tan yellow strands in the rubric. Okay? Coming up with a claim, citing information, explaining information, and summarizing. I just gave them general terms because that same process is what we do in an experiment, and it's the same process that we do in an engineering project. Okay? We come up with a direction, we collect information, we determine if the information or what the information means, and then we come up with a final conclusion. And that's what you do for a CER, that's what you do for an engineering project, that's what you do for an experiment. So ACEs, it's just a good acronym to remember because it guides you. Okay? A, answer the question with a claim. Well, what's your question? This is your question. What are the criteria for a future human colony on an exoplanet outside our solar system? So answer that question as a claim. The criteria for a future human colony on an exoplanet outside our solar system would include... Don't explain it, but tell me what it would need. Okay? For those of you that research the criteria, that's what you're going to explain, that's what you're going to come back to. Those of you that researched 5 different exoplanets, you're going to have to then make a claim that one of those planets is the best possible place to start a colony. Okay? So, the claim could either be oops, stupid question mark, there we go. So claim 1 can be about describing the conditions habitable exoplanet, or both. Pick one of you're going to pick one of those exoplanets to defend for a possible colony. What makes that planet so good? Okay? Cite evidence to support your claim. Pull your research in with your own words. Explain the evidence and how it connects back to the claim. So start explaining. And then summarize, obviously restate your claim, right? I always say, use your good conventions. You should always use transitions, but definitely should have one right there. Transition, then restate that claim. All right? And that kind of helps you set up your outline. All right? And that will be for your final response in phase 4. I would do your A and your C today. Okay? Your A is going to be one sentence. Your C will be a few. So A and C today. I think that's plenty. We'll finish this up on Monday. All right? People doing application B. Experiments require data, qualitative or quantitative, to determine the effect. Okay? For the effect of the independent variable on the dependent variable. This time, you're going to take your images, pictures or Google drawings, and insert them into the column on the left in the table below. And then to the right, you're going to look for key similarities or differences in the absorption lines. So you're going to insert first spectra, insert second spectra, and then so on. Keep going, right? Up to 4. You should have 4 if you want 4 points out of 4. What's a spectra mean? Spectra means rainbow produced when you split light, right? By a prism or by a CD, you can split light, and that rainbow is what a spectra is. So you're just putting them in a line. You're putting them in a column. And then you're going to look for trends and relationships. So some things to think about when you're doing your trends and relationships. What colors were missing? Were any colors brighter in one than another? Maybe I should left align this. So what colors were missing for which? Were any colors brighter in one than another? Were the rainbows different shapes? So you're looking for similarities and differences amongst your rainbows, amongst your spectras. Okay? Because this analysis is going to help you come up with a final conclusion if we can identify light sources based on their spectra. Are there enough differences to really determine it? And if there isn't, will we need better technology? How would this apply to real science? That'll be your conclusion. All right? So aligning your rainbows, looking for similarities and differences. Okay? Application C. I already had some questions from Mr. Kirk by Google Classroom. I'll go through those again if you're watching Ben. But also for the benefit of everybody else, talk about what we were talking about. All right? You are completing your design. You identify the constraints of your design and limit the materials. These parameters will help you to brainstorm, assess, develop a theoretical prototype that would actually be rooted in real life. So you are finally creating a blueprint. Create a blueprint either through Google Draw or a picture on paper. Or there's one more option. You could go to sketchup.com. You would have to sign up. You would have to do try SketchUp, but it is a web-based 3D modeling tool. I'm pretty sure the free version is web-based and not downloaded for personal web only. So you can design something 3-dimensionally. Okay? It's not going to look, perfect because you're going to be limited in different shapes you can use. But definitely, if you want to explore using it, try using it, use something 3-dimensional. Because you're going to be making a blueprint, something that would be 3-dimensional. Alright? So you can try using SketchUp, but if that's beyond what you're interested in. Google Draw or a picture on paper is also fine. For 2 interstellar spacecraft solutions, be sure to include labels and dimensions of your prototype's appearance and materials. Provide an explanation of their operation below. So the couple questions from a couple days ago were, Mr. G, for phase 2, am I coming up with solutions that are the problems that I found or discovered myself in phase 1? No, you were just trying to find all solutions. This phase is you finally narrowing down which solution you like best based on your constraints. Your constraints were phase 1. So, which one of the solutions are you going to go with is the ultimate question, but you're going to pick 2 solutions for the problems that you identified in phase 1. Okay? You insert the picture once it's done. So a lot of your work is going to be away from the box. I mean, if you're doing Google Draw, you'll be in the box, but if you're doing it on paper or SketchUp, you'll come back to this in a little bit. Put your blueprint in, explain how it would work. Explain how it addresses your problems. Okay? Explain how it addresses phase 1. So let me type that in there in case you're stuck. Explain, I don't want to bold it. Explain how your design solution addresses the problems from phase 1. Explain how your designed solution, which came from phase 2, addresses the problems in phase 1. That's what you're explaining. Okay? Obviously this SketchUp, Draw, whatever. All right? What's a blueprint and how is it different from a diagram? That's what Ben was asking me. Be sure to include labels and dimensions. Dimensions is the key difference. I want measurements within whatever you can approximate, how big you want this thing to be, okay? What's small, what's large on it. Include dimensions in your drawing, all right? If you're doing it on a 2D surface, if you are doing Google Draw or a picture on paper, then you gotta give me a top and a side view. Top and side view, okay? With also dimensions, length, width, and height. All right, there's a 4th dimension, time, but we're not going to do that. All right, top and side view, length, width, and height, and then your materials. That's really key right there. All right. Those 3 together come up with 2 spacecraft. They don't have to be manned, which means they don't have to have people on them. They can, but they don't have to. Something like Breakthrough Starshot does not have people on it, for example. Okay. So that's phase 3. I would do 1 design today and do another design on Monday. For application B, I would align your spectra and maybe just do 1 trend or relationship, and then you can do the rest on Monday. Application A, do A and C first. Make your claim, start putting your own research into your own words. Okay? So that's kind of a big overview of what you're doing today. And then I'll review with you on Monday, and then you're going to finish up phase 3 on Monday. All right? So make sure you send me your questions. I can answer them live. Hike. So are we making blueprints for a model or blueprints for a hypothetical real spacecraft? You are making blueprints for a hypothetical real spacecraft. You're using your imagination based on real solutions. Okay? Come up with what you would imagine a true interstellar spacecraft being. Alright? So, it's like I was saying, these parameters allow you to brainstorm, assess, and develop a theoretical prototype that would actually be rooted in real life. So we're using our imagination, but we're also trying to stay rooted in real life. Okay? Hopefully that answers your question. Okay. Any last questions? How big do you think a solar sail would be? the greater the area, the more photonic pressure, the more photons are going to hit it from a star to create movement. So obviously, the bigger the better. The bigger the better. But then you got to be limited materials. Are you going to actually be able to make that much golden foil or that much foil get to space? That would be part of your problems. How are you going to get all that foil and all that material to space? So, I don't know. I would say maybe a couple football fields. Take a look at Breakthrough Starshot. If that's the section you're doing, they're pretty big. I think a few football fields in length and width. But the more area that you can cover, the more energy you could harness. But you'll be limited in materials and cost. All right? Yeah, I'll be over there killed off. Just take one little peek. See, that's an exponential function. Almost. So if you have no other questions, as you're working, if you have questions, send them my way. I'll help you when I can. Tomorrow, if I don't answer them today, I'll answer them tomorrow. Help you tomorrow. If you want to do revisions, help you tomorrow. There is no stream, but I'll be available to help you. Okay? And then, hopefully I'll see you at the Mighty Meetup. Alright? Have a good Thursday. Bye, Nikolai. Bye, Ryan. Bye, Donnie. Bye, Hike. Bye, Rainy.